Okay, so am I audible? Can anybody confirm?
Yes, sir. Audible, sir.
Okay, so let's start this session. It's our last lecture today, and it's an extra lecture. So yesterday we stopped at like we did some questions regarding assignment 12. So I asked you to like try and like if you have any doubt or if you would be facing any problem, then we can discuss. So we can take your doubts for assignment 12 if you have any. So were you able to solve assignment 12? Let's wait for others to join because I
Sir,
received some. Yes, yes.
sir, question 10, question number 10, 11, and 12. I'm not
Question.
able to get the concept behind it, basically.
Okay, okay, no problem. I'll let you know today.
Yes, sir.
10, 11, and 12, right?
Yes, sir. Yes, sir.
That's related to this observer as well as a controller. So did you go through the lectures of
Sir,
NPTEL?
I gone through the lectures, but I'm not able to understand concept of full observer and basically that concept.
Controller, okay. Okay, so let's start with this concept
But
then.
sir, we have different story.
Sorry,
We have different story about this.
you have different story.
Yes, yes, we have got very well idea about this 10th, 11. We don't
So
have
you
any
have
problem.
okay, fine. So you have gone through the lectures of NPTEL, and based on that, you're telling us, right?
No, no, not gone
Or
through
you?
the lecture, but your lecture. I have gone through your lecture.
Okay, okay. So basically, yesterday
And
I only focused on problems.
we have got
Yes.
good marks in these assignments. 10th, 11, like that.
No, no, no. He's not saying 10, 11. He's saying question number 10, 11, and 12 of assignment 12.
Okay, okay.
Yes, sir.
So,
Yes. Yeah.
okay.
Yeah. So anybody else is facing problems, or if you do you have any problem understanding observer or controller, so then I can like just brief you out what it is. Why do we go for an observer or a controller? Why do we design them? And at the same time, did you try that similarity transformation question? Were you able to solve that? There is one question number I think 2 to 7. Question number 2 to 7 is based on similarity transformation. So were we able to solve that question? I like towards the end of yesterday's lecture, I asked you to try solving assignment 12 so that we can discuss the doubts tomorrow. So did you try or have you solved assignment 12 as of now?
Yes, sir. Yes.
Okay, you have solved it. So you faced okay. You faced problems in question number 11, 12. What was
10,
that?
10, 11,
10,
12.
10, 11, 12. Okay, definitely I'll discuss that. And what anybody else?
First, second, third, fourth, then fifth, sixth, seventh, eighth,
You were able to
ninth.
solve them?
Yes, sir. I solved it.
Okay,
10,
nice.
11, 12. I have different problem.
Okay, okay, no problem. So
And
okay, then
two,
let's start. Uh-huh.
10 to 13. 10 to 13. There are 13 questions. I
Okay,
tried for
13
13th
is
also.
simple.
Uh,
Yeah, 13
Hello.
is actually based on the understanding of controllability definition. That's very simple.
Yes.
But this is important, question number 10, 11, and 12, because they describe the concepts of controller and an observer. So let's see, by the time I received some doubts, I received some messages about some other doubts. So by the time they join, we can discuss this thing. So in general, we have this state space system. Whenever we talk of this in modern control, we have x dot is equal to ax plus bu and y is equal to cx plus du. Normally this d is 0, and then we only have mostly yx is equal to y equal to cx. Now the problem is there are two problems. One is, can we this x is the state variable. So x is the state variable, like speed, velocity, acceleration, etc., and etc. So on. Like it depends on the system we have. So now the question is, as we have read in our earlier weeks when we were studying second order systems, we have some input R of S and some output C of S. So we often have this problem of tracking. We give some input to the system and we want our system to track it, right? For example, you might have studied this thing when we were studying underdamped systems or second order systems in general. This is our reference. We give a unit step to our unit step input to our system, and we want our system to track it. So we were getting, in case of an underdamped system, we were getting something like this, right? So we wanted to get this value 1, right? And this problem is called tracking problem. This problem is called tracking problem. So this is problem number 1. That is, we often want our system to track the input, right? So this problem is called tracking problem. Next problem is, that's called stabilization problem. That's called stabilization problem. Stabilization problem means, like, this is state. If we have this state, if my system, so let's assume I have some A matrix, A1, A2, A3, and A4. Let's assume this is unstable. Let's assume this is unstable, then there is no use. Like there is no point in using this. Why? Say, for example, take an example, take an example of a fan. If that is unstable, it means when you turn on the switch, the speed keeps on increasing until it blows up, right? Because when we have an unstable system, the response is something like this. It goes to infinity, right? So there is no point of using or working on an unstable system. Now the problem is, can we stabilize it? If we have an unstable system, can we stabilize it? Right? So this problem is called stabilization problem. You start with a non like unstable system, and then you want to stabilize it, or you start with a system which is stable, but you want to increase its relative stability. For example, if you have a system whose poles are at -2 and -1, if it is a second order system, so you want to improve its stability by taking these poles farther away from the 0, so that it decays down to 0 very quickly, right? So we are improving its stability, right? So this also comes into stabilization problem. So basically, so in a nutshell, to conclude, we have two types of problems. One is tracking problem, where we track an input, and other problem is stabilization problem, where we stabilize the system. So whenever we are talking in this state space system, we are talking, like when I said stabilize the system, I'm saying stabilizing the state X, right? So for example, if I have a third order system, it will be something like this: x1 dot, x2 dot, x3 dot is equal to something something something, like 3 by 3 A matrix, then x1, x2, x3. plus some B matrix, then U. So whenever I'm saying my system is stable, it means these states, x1, x2, and x3. So if I'm saying my system is unstable, it means these states are unstable, right? If I'm saying my system is unstable, it means this x1, it goes to infinity, x2 goes to infinity, x3 goes to infinity, right? Or any one of them goes to infinity, right? So now if I want to stabilize them, or if I want to do tracking, I give some input u and I want my x to track it, right? I want my not x, then in tracking case, it will be y is equal to cx. So in that case, if I give some input u, I want my y to track it, right? So that is tracking problem. But let's say we are solving a stabilization problem. In that case, we should know this x1, x2, x3. Then and only we can control them, right? So if I have an unstable system, I should know the value of x1, I should know the value of x2, I should know the value of x3. Then and only we can stabilize or we can track them, right? Or basically, then and only we can stabilize them. Say, for example, yesterday we were solving a problem of negative feedback, right? State feedback. I used u equal to kx. So when I used u equal to kx, I'm assuming this x is known. This x is known to me, right? And what is this x? This x is state. This x is a state. Now again, come to this. So what you're assuming, this state is known. So for state feedback, you're assuming state is known. And why we are using the state feedback, we want either to stabilize the system. Basically here, we want to stabilize the system. You just assume this, we want to stabilize the system. That's why we're using minus kx. And if you remember yesterday, we were saying design a controller u equal to minus x such that the closed loop system has poles -1 minus j or -1 plus j or -10 and so on. So you would have like noticed we were giving negative poles. Why were we giving negative poles? Because we want to stabilize the system, right? Again, what I said, in order for us to stabilize the system, we're assuming this x is known, right? Now come again to this system, x dot is equal to ax plus bu, y is equal to cx. In this case, my x is state, my u is input, and my y is output. So basically, whenever I am solving this system, I know the solution. I have like taught you what's the solution of the system, e raised to the power 80 minus something and something, right? So this output, this is also called like measurement. So this state can be, for example, velocity or speed, like velocity or like displacement, right? So these they are measured with the help of sensors. So the states definitely like I got some message from Usha Singaram. So how to solve assignment problem 2 to 7? Definitely we'll solve that. I'll give a hint. I cannot solve it because they are assignment problem, but definitely I can help you with some hints. But let me just give you this concept why we are going for controller. So controller is very clear. Why we are going for a controller? Because we want to stabilize the system, right? Our system may be unstable, so we want to stabilize it. That's why we use u equal to minus kx. So we want to stabilize it. Now, what I am saying, for a controller, we assume that our state is known, but this cannot be, like, we cannot have the information of all the state variables. Like we have 3 state variables here, so we cannot have information of all the state variables. You would have noticed normally when I am saying y is equal to cx, the structure of C matrix is 1 0 0, like something like this, or sometimes 0 1 0. It's like this. So what does it mean? What does it mean? See, y is equal to 1 0 0 x1 x2 x3. What does it mean? If I solve it, it implies y is equal to x1 plus 0 plus 0. So it implies y is equal to x1. It means I said this y is measurement. It means we can only measure x1, right? It means we can only measure x1. Similarly, if I have 0 1 0, it means I can only measure this x2, right? So if I have y is equal to 1, 1, 0, it means I can measure x1, x2, x3. So it means I can measure x1 plus x2. So I can measure this combined way, right? So if I have y is equal to 0, 1, 0, 0, yeah, like this, 1, 0, 0, 0, 1, 0, 0, 0, 1. Here x1, x2, x3. Then I know I have all the measurements. I have the measurement of x1, I have the measurement of x2, I have the measurement of x3, right? So when I have this thing, then there is no need. Okay, first let's see. So what I was saying, so normally you do not have full state information. Like here I said this x is a state and we measure it from this equation. This y gives us the measurement of x, and it's not normally available. Full state information is not available. Either only one state is available, or two states are available, or like there are many states, so only one, two are available, right? Why they are not available? Because of cost. See, this x if measurement means we need sensors, or we cannot place sensors at some places where, let's assume, temperature is very high. So we cannot place sensors due to some limitations, and that's why we have limited measurement. That's why this observability concept comes into picture. Observability concept says if we have limited measurement, or if we do not have full state measurement, or whatever measurement we have, and that's not full state, with the help of that, can we recollect all the state variables, right? So if I have measurement of only x1, with the help of some initial condition, can I estimate, or can I get the values of x2 and x3 in finite time? That's observability, right? So if I do not have full state information, then I use another system which is called observer. Then I use another system which is called observer, and which helps me to estimate these states. Which helps me to estimate these states. For example, initially, let's assume I had three states, x1, x2, and x3, and only x1 was measurable. Then I need to estimate these x2 and x3, for which I will use an observer, right? For which I will use an observer. And why do we do this? Why do we do this? A minus bk should be stable, or why do we need to calculate the characteristic equation of a minus bk, a minus lc? It's because of the structure. It's because of the structure of the observer, right? So when you do some derivation, you put on x dot is equal to ax plus bu. If you put u equal to minus kx, therefore what we will get, x dot is equal to ax minus b kx, or x dot is equal to a minus bk into x, right? So this matrix comes into picture. So I can write it like this: x dot is equal to a tilde into x. So it's similar to what I got initially, and bu u tilde, where u is 0, right? Or b is 0, like whatever. So I only have this term, right? So I have an unforced system. We have done this. We have done the solution of this. And why do I want this? Why do I want the poles of the system to be on the left side? Because I want my system to be stable. Why? Because I'm doing a stabilization problem. That's what I said in the beginning. That's what I said in the beginning. That is, I want my states to settle to 0 as time t tends to infinity. That's why I want my a minus bk to be equal to 0. Same goes with the observer. Why would we want unstable states? Then there is no point of using that system which is unstable, right? So basically what you should remember, that there are two types of problems, or you just remember that why do we use controller? We use controller to stabilize a system or to improve its stability, and we use observers. I'll write it. Controller. Why do we use a controller? To stabilize a system. Stabilization. And why do we use an observer? Observer We use observer to estimate unmeasurable states. So is it always possible that we can use controller? Is it always possible that we can use controller, or is it always possible we can use observer? No. In order for us to use controller, our matrix pair A and B, they should be controllable, or our system should be controllable. If my system is uncontrollable, you cannot use u equal to minus kx. If you try on MATLAB, take some uncontrollable system, then use this command. K is equal to place A, comma B, then some desired pole locations. You will see it will give an error saying you cannot place poles arbitrarily at any place because your system is not stable, is not controllable. Similarly, for an observer to estimate the states of the system must be observable. The system must be observable. So these two conditions. There are some other notions. I don't know whether you have been taught that or not. That's called stabilization, or that's called detectability. Stabilizability and detectability. Have you does anybody know it? Like what is detectability or what is stabilizability? Okay, I'll just give you an hint. Yes.
Stabilizable means uh, by controlling some of the state variable, you can able to control the system.
Great. Okay. See, we have just read controllability decomposition yesterday. So let's assume. So in one of our questions, let me see. Of one of our questions, we got answer something like this. When we were doing controllable decomposition, we got answer like this: P A P inverse as 0, -1, 1, 2, 1, 0, 0, 0, and -1. So this was our PAP inverse, and our eigenvalues were 1 and 1 and -1. We said this 1 and 1 are controllable, and this -1 is uncontrollable. Why? Because this is uncontrollable part AC bar, and this is controllable part AC. Now see, I right now said that in order for you to design a controller, your system should be controllable. Right, your system should be controllable. Why? Because we are doing a stabilization problem. As t tends to 0, let's assume I have 3 states. I want my states to go towards 0 as my t tends to infinity, right? So because I'm doing a stabilization problem, see, so I want my states to go to 0, like 1 like this, anything, this, and something like this, 3 states with an inch. So as time t tends to 0, I want my states to go to infinity. Now see, we transformed this system into controllable and an uncontrollable system. So this part is controllable, right? So I can, for these two states, I can use u equal to kx, and my states will go to 0 for these two. But this is uncontrollable part, right? This is uncontrollable part. I said, okay, if your system is not controllable, then you cannot design a controller. But I know similarity transformation, I can convert my uncontrollable system into controllable and non-controllable part. And for controllable part, I can use the controller. Now see, if my uncontrollable part, if my eigenvalues of uncontrollable part, here it's only 1 by 1. Let's assume it was a matrix, -1, 0, 0, -2. Then my eigenvalues would be -1, -2 for this uncontrollable part. Here it's only one term, so it's eigenvalue as well. So if the eigenvalues of my uncontrollable part, if they are negative, right, what does that mean? That means the eigenvalues which correspond to the uncontrollable part are stable. So if that is the case, then it means my system is stabilizable. Okay. So in that case, you see, the state corresponding to this -1, it's already stable. I know I do not need to stabilize it because the eigenvalue is already negative. It's already stable. So I can use controller. I can use controller for this part, and for this part I do not need it. Why? Because the state is already going to 0. The eigenvalue is already -1. So when my eigenvalues of the uncontrollable part is negative, then that system is called stable. You can still design a controller for that, because you don't need to stabilize the uncontrollable part, because that is already stable. Is that clear? Then the system is called stabilizable. So in simple words, you can say, if the eigenvalues, so my system is stabilizable if if the eigenvalues of my uncontrollable part are negative, or if they lie in the left half plane, then my system is stable. Then my system is stabilizable. And what does it mean by stabilizability? Can we stabilize it, or can we use a controller for this? So I said I can only design a controller if my system is controllable, but that's not true. If my system is stabilizable, I can still design a controller. So the stabilizability is a weaker notion, of controllability, right? So if the eigenvalues corresponding to uncontrollable part, if they lie in the negative half, then my system is still controllable, and it's stabilizable actually, and I can still make a controller to stabilize it. Same goes with the detectability. So when you do observable decomposition, I have not taught that, but you can see the similar transformation when you do for observability, you will get AO, but here you will get 0, here you will get A21, and here you will get AO bar. So this is unobservable part, and this is observable part. If the eigenvalues corresponding to unobservable part are stable, then your system is detectable. If not, then your system is not detectable. So any question until this? Let's do one quick problem, and that will also make you understand problem number 2, 3, 4, 5, or 6, whatever that is, based on similarity transformation. I think this will make things more clear. Let's take this system. X dot is equal to -1, 4, 4, -1, x plus 1, 1, u, and my y is equal to 1, 1, x. Now see, what's the question? The question is find whether the system is controllable or not. If not, reduce it to a controllable one. Right? So if it is controllable, then no problem. But if it is not controllable, then reduce it into controllable form. So that's indirectly I'm saying you use similarity transformation to decompose this this uncontrollable system into a controllable and an uncontrollable part, that which I discussed right now. We will also see whether this system is stabilizable or not, right? So whether we can use a controller, or whether we need to see, if the system would not have been stabilizable, then we cannot use controller. Why? Because I can only use controller for the states which are controllable. So let's assume this part was +1. Then whatever controller I use, this state will blow away. Right? Even though my two states are controllable, my third state cannot be, and that can impact the system, and that will create problems, right? So it's very important to see this. Now see, so first of all, what we need to do, we need to find the controllability matrix, that is C. For this, it's a 2x2 system. Then I use B and AB. And what's my B? B is 1 and 1. And what's my AB? AB, when you find, you'll get 3 and 3. So my controllability matrix is 1, 1, 3, 3. We can clearly see the determinant is equal to 0. The determinant of the controllability matrix is 0. It means my system is not controllable. My system is not controllable. Now, when my system is not controllable, I can always like decompose it into a controllable and an uncontrollable system by using canonical forms, right? Canonical decomposition. See, so what I need to find, what I will do now, I will form a matrix P such that my PAP inverse, I should get AC, A21, 0, and AC bar, where my AC is the controllable part and AC bar is the uncontrollable part, correct? But I told you yesterday the procedure like we do not have any procedure to find P, but yes, we can find P inverse. Then P can be found by taking inverse of P inverse, right? So now let's see, let's form P inverse. P inverse should be 2 by 2. So I can take one row, I can take one column from this controllability matrix, that is 1, 1. And I can take second column, any column, as long as my this P matrix, I can take this second column, any second column of P inverse can be anything as long as my P inverse exists or as long as my columns are linearly independent, right? So it's 1, 0 for simple to like make calculations simpler. I'll take simple this 0, 1. Now we can see the inverse exists because the determinant is not 0. Therefore, this is a valid P inverse matrix. So this is like it depends on you. You can take any matrix here unless and until P inverse exists and the columns are linearly independent. Now you can find P. P will be inverse of P inverse. And it's very easy to find inverse of a 2 by 2 matrix, right? So inverse will be this, replace the diagonal elements, interchange them and multiply the off diagonal elements by -1. So it will be 0 and -1, right? So this will be your P. So you got P inverse. Now let's multiply PAP inverse. So when you multiply PAP inverse, what you will get? You'll get 1, 0. Sorry, no, you'll not get this. You'll get 3, 4, 0, -5, and PB will be equal to 1 and 0. Now we see. This is my AC. So this is controllable part. And this is my AC bar. It's uncontrollable part. And this is 0 here. So it's like same as that of this decomposition, right? So my controllable part is 3. So it means if you check the eigenvalues, if you check the eigenvalues of this matrix, your eigenvalues will be 3 and -5. You also had some questions based on controllable and which eigenvalue is controllable and which eigenvalue is uncontrollable. So eigenvalues are 3 and -5. You can clearly see my 3 is a controllable eigenvalue and my -5 is an uncontrollable eigenvalue. So that question is also solved this way. Now, can you tell me whether this system is stabilizable or not? So I can control this state number 1 because that is controllable, but I cannot control state number 2 because it's not controllable. But since my pole or since the eigenvalue corresponding to this state number 2 is in the left half plane, it means it will already decay to 0. There is no need to use a controller for this. So my system is stabilizable. It means my system is stabilizable as well. Is this clear now? Like any problem in this question or any doubt in this question? Then we can move ahead. Yes. Devanand, you had some doubt. Can you now unmute yourself and ask?
Sir, good afternoon, sir. It is
Good afternoon.
3 cross 3 matrix for A and B is 3 cross 2 matrix. Now, how can I solve it, sir?
For which question you're saying?
In the assignment itself, they given A is a 3 cross 3 matrix and B is the
Okay.
3 cross 2 matrix, sir.
3 cross 3 and B is 3 cross 2.
2. Yes, sir.
Okay. Okay. Okay, then. So do you want me to take an example and show this?
Yes, sir. I want an
So there is
example.
one problem. There is one problem in your assignment. It's very simple. You don't have to do anything. See. You'll get some controllability matrix, right? And controllability matrix should have rank equal to 3. Why? Because A is 3. Okay. So, but if this is uncontrollable, then the rank should be less than equal to 3. It can be 2 or it can be 1. If it is 2, it means at least your two states are controllable. So you will get AC as 2 by 2. If it is 1, then you will get AC as 1. And AC bar is 2 by 2. But let's assume the rank of the controllability matrix is 2. So what you need to do, the next step is to convert it into controllable and uncontrollable matrix, right? Then what you'll do, you'll form P inverse. So actually you need to find matrix P, but there is no procedure for this. We will go for like calculation of P inverse. And P inverse, since this is a 3 by 3 matrix, you'll take first two rows. Sorry, you will take first two columns. You will take first two columns of your controllability matrix, A, B, C, D, E, F, and so on. If your controllability matrix would have been 2 by 2, then you will only take one column, because in that case your P should be 2 by 2 only. One you will take from controllability and the other one you will design. But here, since you have 3 by 3, you will take two columns from controllability matrix and third one you will design, right? So you see A, B, C, D, E, F, and this can be anything as long as my P inverse exists, or in other words, as long as my all three columns, they are linearly independent. You can take anything. But if you're like writing an exam, this will always be specified. Why? Because they want same answer from everyone. So they come from the controllability matrix. This should be specified so that everybody gets the same answer, right? So when you get P, take its inverse. You can use calculator or you can use MATLAB for 3 by 3 systems. Take inverse of P inverse, you will get P. When you'll get P, the work is done. Just multiply P inverse, you'll get this form, AC 8120 and AC bar. Now, how to identify the dimension? And similarly here, BC and 0. See, this AC, number of rows in AC should be equal to number of rows in BC. Okay, should be equal to number of rows in A12. So this way you can identify the dimensions of, at least you can confirm the dimensions of AC, A12 and BC. Then number of columns of AC, right? So number of columns of AC should be equal to number of columns of zero vector. This zero vector. Similarly, number of columns of A12 should be equal to number of columns of AC bar. So this is common sense. See, you have to ensure this matrix is compatible, right? So whatever, so I'm saying AC and below this, I'm writing 0. It means this is not 1, 0. This depends on the number of columns of AC, right? If my AC is 1, 2, 3, 4, then my 0 should be 0 and 0, right? And accordingly, if my, now I know the number of rows in, okay, one more thing, number of rows in 0 matrix or 0 matrix should be equal to number of rows in AC bar. So you can find dimensions like this, right? Very straightforward. Now, do you have any doubt? Just if you are confused with the dimension of BC, just see the number of rows in AC, done. Or number of rows in A12. Now, Devanand, you ask. Can you, yeah, can you be a bit
I have
louder?
stuck. Yes.
Yes.
Hello.
Yes. Now.
Sir, I'm solving the problems of like at what value of what different values of eigenvalue the system is controllable on. So, sir, I'm solving the assignments problems and I've got the 3 values of the lambda, right, sir? But
Fine,
I'm
because
just
it's a 3 by 3 matrix.
yes, sir, and I'm using the both the methods. First one is the PVH method, and second one is the symmetry matrix, right, sir?
Okay.
So, but at the according to the value of lambda, if I am solving like if tilted L, it means like T into A into T inverse, then I am getting the matrix where from have good values are controllable and one value is uncontrollable. But
Correct.
by the method of PVH, if I am solving, then I am getting the at lambda is equals to 1. Sorry, it's lambda is equal to minus. 2 columns are similar, sir, right?
Lambda equal to -2, what happens?
Sir, I am getting a lambda is equals to -1, a 3 into 5 matrix, right? And two in 3 into 5 matrix, 2 columns are similar. It means that, sir, the less than rank is less than 3, sir, right? It means that it is not a controllable.
No. See, how many rows are there?
3 rows are there, sir.
Okay. See. You have a 3 cross 5 matrix, right?
Yes, sir.
Okay, what can be the maximum rank of this matrix?
Maximum rank is 3, sir, because it's a 3
maximum
into 5.
Yeah. So maximum rank is minimum of n cross m, correct? So
Yes,
minimum is 3. So maximum rank can be 3. So now what you have to do, it means you don't have to see columns, you just have to see rows.
Okay.
So you have to check linearly independent rows here.
Okay,
But
sir.
it's if you have 5 rows, it's normally difficult to find. So what you do, you just go in MATLAB, just put your matrix and then write rank of that matrix. Have you confirmed that from the MATLAB?
Okay, sir, I'm getting confused because from the simple stream matrix, I am getting the 2 values are controllable, but after verification by the using of PVH, I'm getting this is uncontrollable. Two columns are just similar, so that's why
No, don't see columns. Why would you see columns? Because columns are 5, rows are 3. You just have to see, because rank cannot be 5, rank can be 3 only.
Yes.
At least 3. So rank can be at most 3. So, and one more thing is you just verify your answers using MATLAB, and that will make things clear, because in MATLAB you don't have to calculate manually this rank, and you can just write rank of that matrix, and you just see the answer which you are getting from PBS test is exactly the same you're getting using canonical decomposition.
So you mean that this matrix in 3 into 5 matrix, the maximum rank is 3, right, sir?
Maximum should be 3. It can be less than 3 as well. If the system, if the eigenvalue is not controllable, then it will be 2 or less than 3.
Okay.
So which eigenvalue was uncontrollable? -2. What were your eigenvalues?
My eigenvalues are 0, -1, and -2.
Okay.
Yes, sir. On
And
this
were you getting a controllability decomposition something like this?
0 and -1, sir, for the controllability, and for uncontrollable point is -2.
Yeah. So you're getting something like this, right?
Yes, sir.
Okay. So then PB using PBS test, when you use lambda equal to -2, you should get rank less than 3.
Okay, sir. Okay, sir. I got it, sir.
You
Because
just check it. Yeah.
I'm just comparing the two columns. That way, I
Huh.
get confused. Yes.
Yes. You just see the number of rows, or just go simply in exams. I don't think they'll give you 3 by 3 because it's difficult. You would have seen that
Yes, sir.
if like if your system is not in canonical form, like maybe or the matrix is not sparse, so it's very like involved. The calculations are very involved. But in exams, like we solved a 2 by 2 problem. So they might give you a 2 by 2 problem for controllability, observability, or for state feedback, observer design. They definitely will give you 2 by 2 mostly because
Yes,
the exam is time constrained.
yes, sir.
So
But doing about
uh-huh.
3 questions by the using like one on the one matrix or two matrix, they are giving the 3 questions. So there is some possibility if they will give a 3:3 matrix and they will ask 3 questions regarding according to this
Okay.
matrix. That
Okay.
practicing
But
this.
3 by 3 should also be okay. 3 by 3 is also not difficult because they will give ones and zeros, 1 0, -1 0. So it's not difficult to multiply these matrices involving ones and zeros, right?
Yes, sir.
So with that, I think you can do it. And we have done, I think, 2 problems, and now I think things should be clear. So now somebody, okay, is that okay? Do you have any other doubt?
So I have. Can you give me some hint of the question number 10, sir?
Okay, what is question number 10? I'll check.
Just
Did you?
just this.
Okay,
Just sir, deliberate this question. Question number 10, sir. The question number 11 to 12. Just deliberate, sir.
okay, no problem. Actually, we discussed it in the beginning. You joined late, but again, I'll just give you a hint. So, do you mean the concept, or do you mean the for this like question how to approach it? So, see. First, you see, why do you do this? Why do you do the controllable? Why do you use the state feedback controller? Because I said there are 2 problems. One is stabilization, another one is tracking. So you're doing a stabilization problem. You want your system states to be stable. Like as t goes to infinity, you want your system states to be stable or to go to 0, right? Like this. You want all your states to go to 0. But sometimes your system is unstable or your system is taking more time to go to 0. In that case, if you put poles, you might have studied this dominant pole, right? What we were saying when we were talking about dominant poles, we can only consider those poles which are near to the origin, and we can ignore the poles which are far away from the origin. Why? Because the poles which are far away from the origin, they will decay down very quickly to the 0. So their effect goes away in a very short time. So now if we know more the poles farther from origin, more faster they will decay to the origin 0, or they will go to 0. So and if somehow if my system is unstable, and if I can place my eigenvalues in the left half, if I can do something, if I can add some other system. See, if I have a matrix which has unstable eigenvalues, like right 1 0 0 2, like it has 1 and 2 which are unstable because they are in the right half. So I cannot do anything with this a matrix. I cannot change it. I cannot make it -1 or -2. Why? Because this is my system matrix. I cannot change the system, right? But I can do something else. I can change my input matrix my input matrix B, right? Because that is in our hand. So if I use a different input matrix, or if I use a different state feedback, I can indirectly modify this A matrix without actually changing, like doing anything to the system. So in that case, I should be able to stabilize the system. What I mean to say is that I am placing my poles, which were initially in the right half, I'm placing them into the left half. When I'm placing my poles in the left half, it means my system, as t goes to infinity, will converge to zero, right? So that's the main point why we are doing the state feedback. Now, how to solve these questions? So normally you'll be assigned, you'll be given, okay, place your poles at these locations, -1 or -2 or whatever, right? So you need to identify those poles and make characteristic equation based on them, right? For example, if you're given place your poles at -1 and -2, you will write your characteristic equation like this: s plus 1 and s plus 2 equal to 0, and you will solve it. Correct? Then you will see, you will make this ACL, I told yesterday, a closed loop, which is equal to A minus BK. Do one thing. After this video ends, I'll upload this video to the YouTube. And then you see first 15 to 20 minutes, I'm discussing this thing, why A minus BK should be stable, or why the poles should be in the left half, and why A minus LC, because we have discussed this in detail. Why do we need a controller, or why do we need an observer, and why this A minus, how this A minus BK comes or A minus LC comes. We have seen this, right? So then what we need to do, we need to find this ACL, which is A minus BK, and K should be, my K should be K1 and K2, or K1, K2, so on up to Kn, whatever the number of states be. Then you'll get some matrix in terms of K, right? So you'll get A matrix or this ACL matrix in terms of K. Then what you'll do, you'll do SI minus ACL, make the characteristic equation, put this equal to 0, you'll get the characteristic equation in terms of K, right? Then compare this characteristic equation with the desired characteristic equation, right? Then you'll get the values of K. So for that values of K, you should be able to place your poles at those locations which were specified. This is number one approach. Number two approach is open MATLAB, type matrix A, type matrix B, and type matrix C as well. So then write the desired poles. Let's assume D. Write them. Let's assume pole number 1, P1, P2, P3, so on. Write them like this. Then what you do, you write this command. You need to find the value of K. You write K is equal to place A, comma, B, comma, D. Or you can write, or K is equal to place A, comma, B, comma, this bracket, pole 1, pole 2, pole 3, like indirectly I'll give it here, right? Which will return you the value of K, for which the poles should be at -1, -2, -3, or whatever, right? This is the way of doing it in MATLAB. Similarly, for observer, you need to find L. You can do L is equal to place A transpose, comma, C transpose, comma, the pole locations. Then you should get the value of L. Right? So this is the way of doing it using MATLAB, and this is the way of doing it analytically. Try it analytically first, and then also verify your answers using MATLAB. They're not difficult. They're not difficult. Why? Because if you see the problem, there are only ones and zeros. Like, it's not that difficult. Or it might be involved, but just be very careful and try to do some cancellations. Okay? So does that answer your question? Like, now will you be able to solve that problem?
So I'm getting confused, sir. I just know the concept that you are discussing right now, how to get the
Where you are getting
K2
confused? Tell me.
Sir, but there are two poles locations are given, like A minus BK at something point, and the full order observers at something another poles. So that's why I'm just
Okay, fine.
yes, I'm getting
Where
confused.
are you
Which one?
getting confused? Tell me.
Because sir, there are two poles locations are given, sir. Like A minus BK adds
Okay,
something,
okay,
and another
okay,
full
okay,
order
okay,
observer
fine,
adds something.
fine. See, the question is, wait, I'll go to question. I'll write the question. So the question is, design K such that the control input U equal to minus KX places the poles of A minus BK at -2, -1 plus minus J. This is one part. Then second part is design a full order observer whose poles are located at -5, -4, -3. Now tell me, where are you confused? This is actually one part. This is the second part. They are decoupled. They're not linked. See, first what you will do, you know A, B, C, D, right? And then you will make this A minus BK, or you know the desired poles. See, they are the desired poles. I'm giving you a hint. So what you will write, desired characteristic equation. Desired characteristic equation will be S plus 2 into S plus 1 minus J into S plus 1 plus J is equal to 0. You'll simplify it. You'll get some equation. Is that correct, Devanand?
Yes, sir. Yes, sir.
So this is correct. And then what you'll do, you'll just simplify this A minus BK, put it as ACL. Then what you'll do, you'll just simplify it in terms of K. So then use SI minus ACL, get the characteristic equation, compare the coefficients with this, you'll get the answer. Now for second question, what you have to do, you have only been assigned this. You need to place poles at -4, -5, and -3. What do you need to do? First, you can make the desired characteristic equation, which is S plus 5 into S plus 4 into S plus 3. Now, then what you need to do, you need to write A minus LC, right? This is your ACL, which is A minus LC, right? And now see, be very careful here. A, you know, it's a 3 by 3 matrix. L, as of now, you don't know. Let's be it L, and C is something 1, 0, 0, let's say. Now, based on this C matrix, you know, L, the dimensions of L should be compatible to the C matrix because multiplication has to be done. So what should be the dimensions of this L matrix? It should be L1, L2, L3, and then 1, 0, 0. Why it should be like this? Because my A matrix is 3 by 3. So this matrix should also be 3 by 3. So my L is 3 by 1. This is 1 by 3. 1 and 1 multiplication will happen and the resultant will be 3 by 3. So use ACL as this, A minus LC. Then again do SI minus ACL. Find the characteristic equation, compare that characteristic equation with this, you'll get the answer. I think now you should be able to solve it. Fine?
Yes, sir. Okay, sir. Thank you, sir.
Okay. Yeah, okay. So Yogesh ji, you had some question initially, like, is that now clear? Like, will you be able to do this? 10, 11, 12, or those questions? Yeah,
Sir,
10, 11,
actually,
and
yes, sir, actually, I tried to solve that question previously. I got ACL. I got ACL with 3 by 3 order,
correct.
and there are K1, K2, K3 all possible combinations. In first row, I am getting minus K1, -1, minus K2, 2
Okay,
minus
you mean
K3.
to say K1 and K2, they are everywhere in the matrix?
Yes.
That has to be. Why? You know why? Because your matrix A is not sparse. Your matrix A is probably, your matrix B is probably 1, 2, 1.
Yes.
So if your matrix B is 1 to 1, let me see whether, it's 1 to 1. So if your matrix B is 1 to 1, it means B into K will be equal to 1 to 1 K1, K2, K3. So it will be a 3 by 3 matrix with K1, K2 whole term. So it's very involved. It's very involved. Do one thing. Do one thing. I can understand the calculations can be huge. Do one thing. Do one thing. Use this. In MATLAB, go use K equal to place A, comma B, comma pole locations, and you'll get the answer. In exam, I don't think they'll give they will give questions like this. But yeah, again, in assignments, it's possible, and you can solve it like this.
Yes.
K equal to place A, comma B, and this.
With me, sir. That's why I get confused. Same problem with me, sir. That's why I'm getting all huge equations. That's why I'm getting confused. I'm doing something wrong. That's why I am getting this type of equation.
Yeah, I can understand because you're getting K1, K2, K3, and then they will come in A. Then it's very difficult to find the determinant. Okay, but I think with this you should be able to solve it.
Okay, sir.
There is one more thing. There is, I think, that's called Ackermann formula. Right, Ackermann's formula. But again, that's again involved. There you need to calculate a matrix. Like if it's third order, there will be A cube plus A square, something. So that's again not possible to solve by hand. Yeah, but in exams they'll I think they'll restrict themselves to 2 by 2 only. So don't worry about that. But yeah, you can solve this using MATLAB. So try MATLAB, and then it will be very easy. But of course, try some other problems which are 2 by 2. Now, Usha Singaram had some issues in question number 2 to 7. Let me see question number 2 to 7. Question number 2 to 7. Okay. So they're based on a similarity transformation. So now can you unmute yourself and ask where exactly are we getting confused? Usha? Hello. So can you unmute yourself and tell me where exactly you're getting doubts? Otherwise, because I have already explained it now. We explained it, we like understood it with the help of a 2 by 2 problem. And then also we did some discussion now. So if there is still any doubt, tell me. So those type of questions, what you need to do, you just find, first of all, controllability matrix. Again, it's difficult because if it is a 3 by 3 matrix and there is less sparsity, use MATLAB. If you use MATLAB, you can find this. My controllability matrix C is CTRB A, comma B, right? You will get controllability matrix. Then second step is find rank of C. Right, so rank of C, if it is less than, let's assume you have a 3 by 3 matrix. If it is less than 3, then your system is not controllable. Then and only that controllability decomposition will work. Otherwise, you'll not get such a thing. If your system is fully controllable, then you'll get a different like answer. If you can still find PAP inverse. That's not a problem, but you cannot find the structure like this: AC, A2, A1 to 0, and AC bar. Right? The 0 you will not get because there is no uncontrollable mode. So if in particular you have some doubt, tell me.
Okay, sir. I will try it in a MATLAB, sir.
Yeah, you try in MATLAB. Second thing, for PBH test, sorry, in order to find the controllable and non-controllable like this eigenvalue, first you can get it from here only. Second thing, you can also find using PBH test, which is equal to lambda I minus A, B, use lambda as eigenvalues and see whether rank is less than n, then system is uncontrollable, then that eigenvalue is uncontrollable. This is very, very important, this part, because this is used widely in research or improving the results related to observability, detectability, stabilizability, etc.
Okay, sir, I will try it, sir.
Okay, definitely try it, and I don't think it should be difficult now because we've discussed a lot about this. Any other problem? Anyone?
Thanks.
So definitely you should try to go through this book, C.T. Chen, Linear Systems Theory and Design, right? Specifically chapter 6 for this similarity transformation, and chapter 8 for state and output feedback, and this chapter 6 for controllability and observability. It's a very good book. It explains things in a very nice way. Other questions are basically either you have to prove something, or you have to, some questions are based on definitions, which you should be able to like solve. They're not difficult. Any other question?
Excuse,
Anyone?
excuse me.
Yes.
So can you open the week 9 assignment, sir?
Week 9.
Yes, sir. If you have.
I'll try. Wait. Okay, what's the problem there?
In the first question, sir, I don't know, sir, how to directly solve this type of problem.
Wait, let me see.
According to the graph, sir.
Okay. Wait. Okay, so basically you're given some transfer function, sorry, some Bode plot, and you need to find what you need to find? Type of a system, right?
Yes, sir. Yes, sir.
Fine. Okay, this is a very interesting question. See. Wait. So, okay, let's discuss it here only. Let's assume I am making a Bode plot here, right? Let's only focus on Bode magnitude plot because that's the that only helps you. That only helps us in answering this question. So let's assume I'm getting something like this, some Bode plot like this, right? And there is also whether the system is stable or not, right? Let's assume I make this Bode plot, right? So this is my 0 dB. This is plus, this is negative, this is my minus 180. This is my log of omega here. Now see, now this will be always specified. What is it? Let's assume it's minus 20 dB per decade. Either it is specified or it's already, if it is all drawn on a semi-log paper, you have to check it. See that in that question, I think it's drawn on a semi-log paper, right? Devanand, are you here?
Yes, sir. I am hearing, sir.
So see, in the semi-log paper, you should be able to see when a decade is being crossed, right? So when the decade is being crossed, you should be able to find the slope, right? So,
Yes, sir.
so if you're, if you have, sorry, if you know this, your pole corresponds to a slope of minus 20 dB per decade, and your 0 corresponds to a slope of plus 20 dB per decade. If your Bode plot has an initial, like the initial part of Bode plot, if that's constant like this, if this is constant, it means there is no pole at the origin or no 0 at the origin.
Yes, sir.
Okay.
Yes,
But
sir.
if my Bode plot straight away starts, there is some slope straight away from the beginning, it means there is some pole or some 0 at the origin. If
Yes,
my
sir.
starting point is minus 20 or minus 40, or if it is minus 20, it means there is one pole at the origin. If If it is minus 40, then it means there are two poles at the origin. Similarly, if it is plus 20, then it means there is one pole, 10 at the origin. If it is plus 40, it's two poles at the origin, right? So either it's specified or it's not specified, but you have to check it from the graph. You just observe it. If it is semi-log paper, you see when a decade is being crossed, what is the slope. You can always find the slope, y2 minus y1, x2 minus x1. Points will be specified. There will be points on the x-axis, and the y-axis that will be specified. Based on that, you should be able to find the slope. And then based on that, if it is like in decibels, then you can easily see. Now see how you find the type. If you have 0 poles at the origin, then it means the initial part will be constant. So this is actually the type. Type is given by the number of poles at the origin in an open loop setting, right? So if there is no pole, it means it's type 0. So there, in that case, the Bode plot will be like there will be a there will be straight part, like there will be no slope change in the beginning. Let's assume you have a type 1 system. It means there is one pole at the origin. So in that case, your Bode plot will start like this, minus 20 dB per decade, right? So just by looking at the Bode plot, and you should be able to say what is the type of a system. It's not difficult. Now one more important thing. How to check stability? See, what is this point? This frequency, this is gain crossover frequency, right? This is omega GC, right? Omega GC is the frequency where my gain becomes 0 decibels, correct? And what is this frequency? Omega PC is phase crossover frequency. So in order for you to check stability, what you need to identify, gain crossover frequency and phase crossover frequency, right? So my phase crossover frequency is this. My gain crossover frequency is this. This is my phase crossover frequency, right? So whenever teaching you gain margin and phase margin, you need to check the value, the magnitude at phase crossover frequency and the value of phase at gain crossover frequency, right? This is the values. And I told you this region, my gain margin, phase margin is positive. This region, my gain margin is negative. Similarly, this region, my gain margin is negative. If my gain margin is negative, then like if I have this point, then my gain margin is negative. And if I have my point lies somewhere here, then my gain margin is positive. Why? Because I have gain margin something like 20 log of something. It's already minus. Then that's why it's going the opposite sign. So now for a stable system, both the gain margin and phase margin should be positive. So if both my gain margin and phase margin are positive, here you can see my gain margin is negative and my phase margin is negative. My system is unstable, right? So for a stable system, your gain margin and phase margin both should be positive. And for unstable system, they're negative. For marginally stable, they're 0. Now, can you tell me what is the gain margin for a second order system? Have you read it? Can you tell me what is the gain margin of a second order system? So this is my second order system. I'm writing it closed loop transfer function of a second order system. Omega n square, s square plus 2 zeta omega ns plus omega n squared. This is my second order system, right? So if you solve this, you'll find two roots, right? And based on this, the roots will be, it's a quadratic equation. If you solve it, the roots are in terms of zeta, like the solution will depend on zeta. If my zeta is less than 1, my system is called underdamped. If my zeta is greater than 1, my system is called overdamped. If my system is equal to 1, my system is called critically damped. And if my zeta is 0, it's undamped. Now, When my system is underdamped, my pole locations, this is only second order system, there are only two poles, my pole locations are somewhere like this. When my zeta is overdamped, my pole locations are somewhere like this. When my zeta is critically damped, my pole locations are repeated on the origin. When my zeta is undamped, my pole location is, but that's not the case. Like only three cases arise here. Either it will be less than 1, greater than 1, or equal to 1, right? So I get three possibility, three scenarios, but in every case, my poles are in the left half. My poles are in the left half. What does it mean? My system is
Stable, sir.
stable, but all the time. So these second order systems, they are always stable. So when I say my second order system is always stable, then what is my gain margin for a second order system? So see, gain margin, if I define gain margin is the amount of gain that is required to take my system to the verge of instability. For example, my system is stable. I increase its gain, it will become less stable. I again increase its gain, you will check it from Bode plot, it then reaches to marginal stability, right? So when it reaches, then again I increase the gain, it becomes unstable. So the amount of gain, when it reaches to the marginal stability, this is called gain margin. But if I see my second order system, like when I increase the gain, nothing happens. My system is always stable. So in that case, my gain margin will be infinity, because you cannot like have enough gain to take the system to the verge of instability. So if my gain margin is infinity, it means the phase plot of my second order system will be something like this. So it will this phase crossover frequency, that will be infinity. Why? Because my phase crossover frequency, that gives me the point to calculate my gain margin. So when gain margin is infinity, it means my phase plot. Will you try this? Take any second order system, you'll see your phase plot will be something like this. The gain margin will be at infinity, right? So is that clear, Devanand? Just do some practice and I think things will be clear. Yes?
According to the graph, sir, I didn't understand anything.
This graph?
Yes, sir.
So
No,
have
sir.
you...
Sir.
The graph which I explained earlier?
Yes, in the assignments graph, I am just looking the point where it will cut the zero dB lines, and it will cut the 180 dB lines. According to that, I have just
Of
found
what?
that margin is positive and
Stability?
negative. Yes, sir. Stability and the type both. So stability, sir. Yeah,
No.
stability. Sir, record.
Your voice is not coming. Hello?
Yes, sir. I'm audible, sir.
Now you're audible. Now tell me.
Sir, according to this graph, I am not able to give the direct answer. This is a stable or not, sir. Or what are the
Why?
type of...
Why? No, okay, yeah. From this way, it's not possible because this is not drawn on semi-log paper. Then things have to be specified. But the assignment question that's drawn on semi-log paper, you should be able to give answer on that. But for stability and instability, you should tell here whether your system is stable or unstable, because I have specified gain crossover frequency and phase crossover frequency,
I know, sir, but according to this graph, sir, the zero dB lines is cut is the approximately it is after the zero dB line, sir. It is like 180 dB line. But if I will see according to this graph, then approximately 10 to the minus 1, it will cut the 50 approximately 46 or something like that. Then omega GC is
How do you know?
negative.
I have not mentioned any value. See, but you know this thing in my here, omega PC is less than omega GC. So what does it mean? If omega PC is less than omega GC, is my system stable or not?
Sir, according to me, sir, omega GC is less than omega PC, then it is the more stable, sir.
Is it more stable? How?
According to the controller design, sir, I am getting that type of...
No, like just share it. Like We'll see. Like how you have, like, which lecture you have seen?
Sir.
So some book you have, whether this is being explained.
So
If
I'm not directly saying, I will say like eta omega pc is greater than this. But according to the graph, you will. I've just watched your lecture, and you are saying that just see where it is coming 0 dB line and where it is coming
yes,
in the dot 1 degree, 180 degree line, right?
yes,
So
yeah, that's it.
yes, sir. According to this, if I am seeing that, then it will cut approximately 180 dB line is approximately, and at that point the omega gc is negative, sir. According to this graph, omega gc is negative.
Where?
So
Which
according to
point? Which point? Which point? Minus 180.
yes, sir.
This point?
Ma- Sorry, sir, but I'm not. I'm not deliberating all the things according to your graph. I am just listening. I am just watching the assignment question, sir. Question number
Okay,
one.
fine, no problem, no problem, no problem. But see, how can omega be negative? Because omega is drawn on this scale, right? Omega is drawn on x scale, log scale.
I'm talking about omega PC, sir. Like at that point.
Whatever. How can that be negative? That's frequency, right?
Sir, sorry, sir. I'm phase margin and gauge margin. Sir, so sorry. I'm talking about phase margin and gain margin, sir. Phase margin,
Okay.
according, sir, at this point, omega GC, where you have mentioned in the black
Okay.
dotted. So at this point,
This is
omega
omega.
phase negative, sir. Phase margin is negativeness. Omega GC, omega PC, sir. Omega PC at point, the phase margin is negative at omega PC.
No. Who told you phase margin is negative here? At omega PC, it should be 0, right?
Yes.
So here
Yes, sir.
in this graph,
Yes, sir.
in this graph, you will not check when, see, what is phase crossover frequency? Phase crossover frequency is the frequency where your phase is minus 180. And what's your phase margin? Your phase margin is 180 plus phi, right?
Yes, sir.
And phi is the angle at the omega at the gain crossover frequency, and that's also minus 180. So it's 0. Phase margin is 0 here. So at this phase margin is 0. Similarly, at this gain margin is 0. Not 0 exactly, because then you have minus 20 something or something. But yeah, phase margin is 0 here at minus 180 at omega PC in this graph. Okay, no
Yes,
problem.
no,
You
sir.
just
Actually, the values that you are discussing, that means whatever graph you have shown, you have shown WPC with that round point that you have shown. WPC, that means the phase crossover frequency, which cuts the plot at minus 180. Okay, at that
Yes.
point, whatever gain margin you are calculating, that is above 0 dB line. It is
Yes.
negative. That's why it is
Yes.
unstable. That's what I think Dayanand is saying.
Are you saying that?
Yes, yes. The same thing he is
So
saying, but he was
oh,
not
that's
using proper words for the questioning, basically.
okay. Okay.
So in this case, system is unstable because your gain margin is negative in that case.
Yes. Yes.
And
That's what
here
I
also
said as
your,
well.
yes, yes. And
So
your phase
that they,
margin is also negative. So both are
yeah,
negative,
phase margin is also negative. So my system is
also negative.
unstable.
Unstable, yes.
So Devanan, is that
Probably,
clear? Yes.
Yes, sir.
prob-
Clear, sir. I am already told you. But in this graph, sir, in the assignment questions, at this point where it is cutting minus 180 degree line,
No matter. It can
degree
be.
lines.
It can be like anything. I just made this graph just to make you understand.
Sir,
It's not
but
necessary the assignment.
at this point, sir, at any position, if we are seeing that, then gain margin is negative, sir.
Yes.
And gain margin is negative, it means that, sir, this system is unstable.
yes,
Yes.
sir, yes, sir.
Sir, but
Sir,
Yes.
assignment,
actually,
this is just 7. That's why I am
sir,
getting confused. How?
And
what
in
Dayanand is
assignment, what
asking,
happens?
question
That's
number 2, they are asking, is the closed loop system is stable? Even I
Okay.
also written that it is unstable, but they have given
Okay.
that this is stable. That means though we are giving the correct answer, they evaluated the answer wrongly.
Okay.
yes,
So
sir.
that's
Maybe.
what
Maybe. Okay. Okay. That. Okay. Okay. I'll
question
check
number
that.
2.
I'll check that.
And
So
and even that graph is not clear cutly mentioned कि वहाँ पे 180 लाइन को वो कट नहीं हो रहा है बेसिकली, तो इसलिए वो थोड़ा सा कंफ्यूजन वहाँ पे हो रहा है. And as the same question in online interaction, I think it was another online session by different teacher.
Biswajit.
Yes. So I asked this question. He told me that I will check it. That means he will check it. But after that, I never asked him, and he never told me because we don't hide with that week.
Okay.
Yes.
See, whenever you have to see gain margin, you will look at phase crossover frequency, and if your gain margin is positive, then your system is stable, and as well as the phase margin is positive. But if here in this example, okay, what is in the assignment problem? Let me see.
Question number
in the
1.
assignment problem,
Yes, sir.
okay.
This question, sir, because they are just confusing us. He just asking about that question.
Phase crossover frequency, the gain margin is, I think, positive. If you zoom it, do one thing. Is there given any transfer function? No, they have not given any transfer function. Okay, and they have also made it asymptotic, not asymptotic, like it's actual body plot, and it's not visible properly.
Yes, and from 0 dB line also, if you are observing 0 dB line, because 0 dB line you can find
0
out.
dB.
तो 0 dB line से आप वहाँ पे phase
0
निकालते
dB
हो.
gain margin. Okay, at gain crossover frequency, it's exactly, I think, coming minus 80 or less than that. It's very difficult to see, actually.
Yes, difficult to see.
But don't worry. Maybe there is. What have they written in the solutions?
They are asking if the system is stable, but we have given the answer it is unstable.
Okay, and they have written it, it's stable. Why? They have written the reason?
Yes. No, reason is not mentioned. They are giving only answer. Yes, no, yes.
There can be a mistake. There is no problem. You just write them that can you give proper justification why, how is it stable? Because see, if my gain margin is positive, phase margin is positive, because looking at this transfer function, if you're able to conclude your phase margin is positive and gain margin is positive, your system is stable, period. If any of them are negative, then your system is unstable. So you just have to check that.
Yes, okay, sir. वो confusion तो sir सही है कि मतलब वो graphs clear नहीं था, but according to that, sir, how I can say that this is a type 1 or type 2, sir, because it will starting approximately 180 dB, and according to that, we can directly say, I don't know, sir, exactly what happened. Like
where? Which graph? Which graph? Above or below?
Yes, sir. Magnitude graph, sir. Magnitude जो dB में दिया हुआ है.
Magnitude graph, yes. This graph. So yeah, what are you saying about this?
So according to the assignment, it is starting from the 180, approximately 180. Then how I can say that this is the type 1 or type 2, sir?
Doesn't matter. That can start from any point. That value depends on the value of k. But you have to see the slope. You just have to see the slope. See, okay, wait. Yeah, this is a good question. See, let's assume this is 180 here. This is what you are saying? It's not degree, sorry. It's 180. 180 dBs, right?
Sir.
Right?
Yes, sir.
Devanand?
Yes,
no,
sir.
Let's make it like in a
sir,
different.
Can you show assignment number 9, sir, on your screen? Then more it is good for us, sir.
Okay. Wait. Then I need to unshare this screen. Then I cannot write because I'm writing on my tablet and that is opened on my PC. I'll just make it. Wait, I'll just make it assignment. Wait, okay. First, I'll clear it out like this. See, this is, let's assume it's something like this. And this is 180, right?
Yes,
and
sir.
This is 0 dB. But you know this value as well. This you know all these values are specified, right? All these values are specified. Let's assume this is 1 decade. Let's assume this is 0.1 and this is 1, right? This is 1 decade. So you know now what is happening to the slope. You know this value, you know this value. Let's assume this is 150. You know this. So can you find the slope here?
Yes, sir.
Yeah, you can find the slope 150 minus 180 divided by log of 1 minus log of 0.1. This is your slope. Done.
Yes, sir.
If your slope is 20 dB per decade, because this is 1 decade, if your slope comes 20 or minus 20, then
Yes, sir.
you have a pole at origin. Definitely this is not a type 0 system because there is some slope from the beginning. So this
Yes,
can be either type 1, type 2, and so on. So if you are getting minus 20, then your system is of type 1. You just have to find the slope in one decade. Now I'm going to assignment problem. In assignment problem, you can start from, or they have not mentioned, okay, I think they're starting from 10 to the power minus 5 and 10 to the power minus 4. And see, the initial value is roughly 180. And at the end of decade, it's around 140. Is it? Is it like that? Like, I think your initial value is 180 and other value is 140, and you have log of 10 to the power minus 5, and this is log of 10 to the power minus 4. Is it the case? So now you can find the slope. You just don't have to see the phase plot. That's it. Is that
Okay,
clear?
sir.
I think
Yes,
there
sir.
is no slope changing. What have you written? What had you written in the answer?
So I just without any solution, sir, I've just written one, but the answer is two, sir.
You just find the slope. I think if answer is 2, the slope will come out to be 40. Okay, let's solve it. Let's try to solve it. It's actually, there is one problem. They have not accurately given the values. You just have to assume. So let's try to find the slope. So it will be 140 minus 180 divided by log of 10 to the power minus 4 minus log of 10 to the power minus 5. So let's solve it. That should be our so it will be minus 40 over this.
Yes, sir. It's minus 40. Then it means that it's type 2.
Is it coming now? Yeah.
Yeah.
Yes, this will be 1. Yeah, it's minus. Yeah, it's type 2. Now is it clear? You just have to check the original slope. Okay. Then
Yes,
whatever
sir.
happens after that, you don't care, because
Okay.
after that you just have to see where the slope is changing. That will be your corner frequency.
Okay. And about
But
the
yeah,
stability, we will go the
yeah,
concept, same concept, right, sir?
you will go the concept. Sorry.
Same concept, sir. It omega PC negative,
Yeah.
like
Yes.
gain margin.
Just locate omega PC and omega GC. Just see whether my gain margin is positive or negative, and then conclude. If they are positive, your system is stable. They are zero, system is unstable. System is marginally stable. Positive, negative, system is unstable.
According to the answer, this answer is wrong because this is an unstable system, sir. Because gain margin is at that point is negative, sir. But they have
Fine.
given that
Yeah,
this is system.
it can be. So that's not a problem. They can give wrong answers. That's very
Sir,
common.
and
Uh-huh. Your voice is not. You're not audible. Can you come again?
read the question number 3 and question number 4.
Hello. Can you come again? Am I audible? Hello. You're not audible, Devanand. Hello. Yes. Hello.
I'm audible, sir.
Yeah. Now you're audible.
Sir, please explain the question number 3 and question number 4 of
Of the
this.
same assignment?
Yes, sir. Yeah.
Okay. What is the acceleration error constant of the system? Okay. Again, there are many ways to solve it. One of the ways, shortcut says, you just have to check, since this is a type 2 system, you just have to check where is the 0 dB crossing. That point, take the root of that, you'll get. I think what have they written in the solution? Wait. Okay, it's a blank question. Oh, they have also provided the solution, right? In slide
sir.
number 12 of lecture 1, module 9, it's derived that the acceleration constant for a type 2 system is given by, yeah, this is what they have derived. So according to this is a shortcut, and I think many people, they teach it like this, KA. But you know, there is, have you attended my, this lecture? I think 10 lecture.
Yes, sir. Now I got it. How to,
Experimental,
yeah,
yeah,
it's a value or where it is coming, like it's a square root of k, like that. And
yeah.
if it,
One thing is like this. Yeah, you
yes, sir.
can do it like this. Then easily you can find the steady state error,
Yes,
right?
sir.
Unit ramp 1 divided by kV. So sorry, it's a unit ramp. So it should be there. You just put the value, like use a steady state formula. But what I'm saying, when we were doing week 10 assignments, there was one task was to find the transfer function from the body plot. Did you attend that?
Yes, sir. I have attended that one, sir. I have
Yeah.
watched the
So,
YouTube.
so there, you know how you find the value of k if you
Yes, sir.
have a first order system or a second order system. You know, there you see this initial frequency.
Yes,
So
sir.
based on
At
this, yeah,
yes,
it's like 20 log of k minus r, that gives the number of poles at origin, into 20 log of initial frequency. This is equal to the magnitude gj omega, right? So based on this formula, I think you can also find the answer. Okay, anybody else has any question? In assignment 12, because you would have got the answer, got your marks till assignment 11, right?
yes, sir.
11? Okay, fine.
Yes,
Only assignment 12 is left.
yes, sir.
Okay, so assignment 12, I don't think now there is any problem, because whatever tough questions are there, just solve them using MATLAB. One thing.
Assignment 11 is Suiji, and assignment 12 we know also good Suiji, sir. Because I got 100% in the 7th assignment from the last previous 7 assignment, but I'm facing problems the last two assignment, because I don't know the feedback, output feedback, that type of concept. That's why.
Oh, that's what I explained in the beginning. Or are they not explaining it in the lectures?
Sir, they are just reading the PDF, sir. That's why I get bored how to know the concept.
Okay, fine. Okay, after we finish this lecture, just go through first 15 to 20 minutes. I explained feedback, I explained observer, what's the need,
Sir,
and also,
sir, one more doubt, sir. So sorry, but
yes, yes,
in the assignment, it's assignment 9. Can you open? Can you
okay,
open the assignment, sir?
yes, tell me.
In the question number 8 and question number 9, sir, I have just draw in the board in the MATLAB, and according to that, I have just saw the graph, and according to that, I have answered the questions, but my answers is wrong, sir. But so I don't know how to solve that type of problem, sir. And according to your solution, like you are saying that how to solve that type of problem, so I have just made the equation, and that equation is very difficult to solve in the time domain. So according to that, sir, how I calculate the answer, sir, in the steady state output?
What are we designing? Wait,
Assignment
okay,
number
it's a common
10.
question. It's a common question. You're given a transfer function. What's the value of
Yes,
k? That will result in an error constant. That's fine. KV, we have to find. That's very easy. S into that transfer function. Okay. With the choice of k, this is fine as well. And you have doubt in question number 8.
yes, sir. Assignment number
Lead
10.
compensator. 10.
Yes, sir. Assignment 10, sir. I'm talking about assignment number 10, sir. Not
What is the
other.
question? What's the question? Can you read it?
Yes, sir. The question is that the consider the system with transfer function. Transfer function is given. in the form of numerator. Each of the order is 3, and they are asking about like it is starting like a wrong direction and the correct direction, and again they are asking about the steady state output of the response.
Just give me 1 minute. Wait, I'm just opening. Okay. You're given a transfer function. Fine. Then they are asked the possible number of zeros in the RHP of this, right? Question number 8 and 11.
8, sir. Yes, sir.
8. Okay. Then they are asking the steady state output to a step response, right?
Yes, sir.
Okay. Then they're asking, your doubt is when a step input is applied, how many zero crossings will appear in the response, right?
No, sir. I just clear because how many zero crossing? Because they are just we have to see that where they are crossing the zero. But the steady
I
state.
I got it. You mean to say the time?
Yes, sir. Because very difficult
that is
to
a
find.
bit difficult. That's a bit difficult. I don't think they'll give you. It's very difficult. You can find that using MATLAB only. I have in my videos as well. I have showed that use MATLAB or just plot and you'll get the answer, because it's very difficult to solve by hand. You'll get so many big equations and solving them, and they're called transcendental equations. Sometimes calculators, I don't know whether that scientific calculator will be able to solve that, but yeah, in general that's very difficult to solve by hand.
Sir,
And
but
that's very obvious. They will not give it.
I've just drawn in the MATLAB, sir, about this transfer function. At the starting, it is instant, sir, according to the MATLAB, and after that it is going downwards, right, sir?
Fine. Okay.
According to the MATLAB, I have just drawn this transfer function. I am getting the in the time response. The starting it is the constant, and after that it is getting downward.
Okay.
And sir, and as per the concept, this direction is in the direction of the wrong direction, sir, because it is going downward direction. So we can say that this is wrong direction, but the answer is this is the correct direction, sir.
Are they asking about the direction as well?
Yes, sir.
See, do you mean your answer is something like this?
No, sir. At the starting, it is constant. At any
it's
point,
constant. What is the value? Do you have initial value?
Okay, sir. Can I 1 minute, sir? I am just seeing the pictures if I have.
Just see, because if it's something like this, it's going to infinity, right? Negative infinity. Just send me through WhatsApp. I'll make it for everyone.
Let me check, sir.
Have you read that paper which I had sent?
Yes, sir.
Based sir, on that as well, you're getting the.
1 minute, sir. I am just drawing on the paper. Okay. Like at the is a straight word,
take photo and send me.
Okay, sir.
How many zero crossings are there?
It's 3, sir. It is correct, sir.
That's
according
fine.
to the answer, yes, sir.
Okay.
I've sent you in the WhatsApp, sir. At the starting, it is constant, that it is going downwards, sir. What is the direction of, according to the question, what is the direction? What should I answer, sir? Okay, wait. You have again sent a partial period. Do you know the values? Sir, do you know the value initially? So it's see, where should it be? It should settle somewhere, right? Like yes, it has to track some, it has to unit, they're saying unit step, they're applying unit step, right? Yes, sir. So it means it has to settle at 1, right? Yes, sir. So from wherever you start, if you are moving towards 1,
then you are going in a correct direction, right? But you are saying it's constant.
Yes,
But
sir. At the start, it
if
is
you
constant.
zoom in, you see initial value, or you just see the value of that trajectory x, right? So
Yes.
then you see it will not be it might look it's constant, but it's not constant. So it might be going through the correct direction, I think. So if there
Sir,
are
I am.
three zero crossings,
Sir, excuse me, sir.
if there are three zero crossings, it will initially go in the correct direction, then it will be constant, then it will go in the wrong direction, then again constant, then it will again go in the right direction. But for three zero crossings, initially it will go in the right direction. You check it.
Sir,
Either you have plotted it wrong,
sir,
right?
excuse me.
Uh-huh.
Sir, I have sent you in the WhatsApp the exact graph, sir.
Oh, I think no, I don't think. Is it like? Oh, it seems strange. I don't think it will come like this.
Sir, I have drawn in the MATLAB, sir. I have just
Show me
written
the
right.
transfer function. Show me the transfer function. There must be some mistake in the transfer function. And
Just
your unit step, you are tracking. You see, it's settling at 2.5 or 1 point. Like it's settling at 2.
give me some
Your
time, sir.
have you
Sir,
like
give me some.
have you used MATLAB or Simulink? Tell me that.
Sir, MATLAB, sir.
MATLAB. Okay. Now show me what is the transfer function. Is it the same as what is given in the like this, in the question?
Sir, give me a chance and
Yes,
answer
yes,
the
please.
question. That's give me some time, sir.
No problem. No problem. Okay, it's not a problem. I think there is one negative sign as well. So I hope that you have put that. Or just see it, and you have to give unit step input. Right. So accordingly, I think
Yes,
it
sir.
should be correct. By the time anybody else, if anybody else has any question, I hope there is no question related to assignment number 12. If there are still, because we are in touch with this thing, like assignment 12, so we can do that. And otherwise, if there are problems, if you have solved some question which you think is correct, but you have got wrong answer, maybe you have done some mistake or there is some problem like in the solution. And I would recommend every one of you, whenever you're solving any assignment, try to use MATLAB and try to cross-verify your answers, because that will give you more confidence. Because whatever you're solving analytically, if you are also able to solve that using MATLAB, that will give you more confidence, and you will remember like those concepts for a longer time. And also you should also at least go through the slides which they have shared, the NPTEL people, because your exam paper that will explicitly be based on that only, from your assignments, from those slides, and whatever they teach. Even if they teach like easy stuff or difficult stuff, you have to follow that. So be very sure to refer to those slides, at least, because lectures, I know it's time taking, but yeah, for slides, I don't think they will be. So anybody else has any question by the time Devanan comes with?
Basically, now I am having problem in lead lag compensation. And
Okay.
Bode plot I can able to do it, but in lead lag
Okay.
facing problems whenever I am
Okay.
trying to attempt it.
Okay.
Even I got
How many
one
marks you got in lead lag?
lead lag assignment. I got 50% marks in that assignment.
Okay. 50%. And
Lead
what is
lag
the passing marks?
passing marks are 40%. 40% for passing.
Okay. That's fine. But one thing that this course is a bit advanced, because normally this control course, it stops at leak lag, compensator design, and only using root locus. That should be that, and that's easy, I think. And after that, using Bode plots, gain margin, phase margin concept to design, it's a bit tricky, and at the same time, it's a design problem, so it can have multiple answers. And if I give questions to 10 people, design this using design a lead compensator or lag compensator, 10 people will come with 10 different answers, and every answer is correct. And it only depends, okay, how much better it is. It's not like the answer is wrong or something, but yeah, it's in that case we have to see which answer is better. But in these objective type questions, they specify you something. They give you some things which you have to take into account, and based on that you have to answer the questions. When I taught that in a general setting, but in that case you have to choose some angle, 0 or something, and then you'll get the answers. But again, if you go through the lectures, I think that should not be that difficult, because already you don't have to spend more time on time domain analysis, stability analysis, root locus. So if those things are already, them pretty well, you only need to focus on this control design. I think that should be fine. Just invest some more time in that. The state space is also easy. And you would only be like needing time to solve those problems. And that's one lead lag design using root locus. That's also easy. And the other one is root locus design using using polyplots. But I don't know how they will give in the assignment, because they are very lengthy questions. They will give some short
assignment
questions.
number 8 and 9 are somewhat we find
Advanced.
very much has not vast as such, but needs to study more and more on that.
Yes,
The way by
because
which,
see,
yes, the way by
root
which they
locus.
this
Uh-huh,
in your session, I I
uh-huh,
I have missed the initial sessions of yours. That's why I
uh-huh.
lost my that's why I lost good interaction with you at initial time of this course.
Okay, you joined
Otherwise,
late. You joined, I think, in section 5 or 6.
yes,
You
yes,
didn't
yes,
join
yes,
from the beginning.
yes,
And after that, I think you are like regular.
yes, sir, yes,
So you just spend some more time.
yes,
This
sir, yes, sir.
thing.
I will
Uh,
personally
we,
contact you. I will personally contact you through WhatsApp. And
no problem.
if possible,
Uh,
you give me time for that. If not possible,
yeah,
just you put message. No problem.
no problem. I'll try to make some question or write that in a manner which is self-explanatory. And
Okay.
or I'll see some assignment question which is there in the quiz. Have they released answers for week 8 and week 9?
Yes.
They must have released that. You first go through them, go through those questions, try to understand them. And
Yes.
after
Yes.
that, if you're not able to understand, then yeah, you can always contact.
Okay, sir. Okay.
Mm. Anybody else?
No, sir. I think he is also on the phase right now.
Yeah, so
Devan.
anybody, yeah, Devanand, except from Devanand, anybody else has any questions? Otherwise, we can just stop the recording. It's just like not fruitful. Otherwise, we can continue the discussion, but yeah, I'll just stop the recording.